Today I'm going to present a method on single-cell sampling, and this is a shared work with Khaled El-Bassani and Stephen Kansan. And recently, single-cell RNA sequencing has become a favorite choice for studying the key biological questions of cell heterogeneity, cell differentiation, and development. Single-cell RNA-seq, for example, can identify and reveal the complex and rare cell population, or it can check the trajectory of the distinct cell lineage in development. And bulk RNA-seq technologies has been widely used to study gene expression pattern at the population level in the past decade, and it measures the average expression level for each genes across a large population of cells. And it's useful for comparative studies, such as comparing the tissue between two different conditions, healthy versus disease, for example. But it's insufficient for studying the heterogeneity system, such as early development or complex tissue. In contrast, single-cell RNA-seq can measure the expression level for each gene in a single cell. Therefore, it can answer the new biological questions in which cell-specific changes in transcriptome are important, such as cell type identification or heterogeneity of the cell response, and so on. And there are a lot of technological development since the first single cell published in 2009. So if you look at the year in the x-axis and the single cell in study in the y-axis in this exponential scale, you can see that the size of the data grows exponentially. And now we can provide up to like millions of cells. And therefore, this is one of the most challenges in single cell data analysis. And you need very, very fast algorithm. We can handle very, very big data. Or alternatively, you can make the data smaller. So this problem is called subsampling or downsampling in some context. And this is also the problem we focus on today. So we want to make the data smaller. And one of the most commonly used sampling technique is random sampling. And the idea is very simple. Let's say you have a data set of like 2 million cells, but your favorite algorithm cannot handle like 1,000 cells. And then you just select 1,000 cells out to 2 million cells at random. So of course, it's very fast. However, it's prone to the removal of the rare cell type. And that we want to avoid, right? And there are data-dependent sampling techniques, such as k-means or spatial random sampling. These methods are more accurate than random sampling. However, they do not scale well to large data. You know, I already mentioned now we have like millions of cells, right? So we cannot use the algorithm. And recently, symmetric sketching was introduced as an alternative way to uniform sampling. And they show that it's very fast. And most importantly, it consistently outperform better than random sampling and data-dependent sampling techniques in a large number of downstream analysis tasks. And the idea of symmetric sketching is that it selects a subset of cells and they call it a sketch, such that the hold-up distance between the sketch and the full data is minimal. So let's take one example here. And here the cell in sketch are marked with the black circle. So the red point here does not belong to the sketch. And the hold-up distance is defined to be the distance from the first point here to the sketch. So if this is small, right, then the distance from the other point to sketch could be small as well, because this is the upper bound. So in the other word, the low hold-up distance indicates that every cell in the data are close to some cell in the sketch. And the key idea behind this approach is that it's sampled by the symmetry instead of the density. That's why it could lead to more balanced composition of cell type in the sketch. And for example, let's say making the red cell type easy to be detected. Unfortunately, this problem is NP-hard. However, how does the symmetric sketching solve this problem? And the main idea of symmetric sketching is that they cover the space by the non-overlapping boxes, and then they just pick one cell per box. And in particular, they use a strip here, as you can see in the figure, or they also call it a plate to cover every cell in every dimension, like this. And in here, you can see that two consecutive plates here, they are put far away from each other as long as they don't miss any point in between. And they repeat it for every dimension. And you end up something like this. And from each square boxes here, you just pick one point per box at random. So this is the main idea of symmetric sketching. And you can see that this is independent of the distance matrix we define in the object function. Therefore, one of the main problems of symmetric sketching is that they have no warranty on the quality solution in general. So our goal to minimize the same objective function, in particular the Haldor distance. But the way we solve it is different from symmetric sketching. And most importantly, we have a theoretical warranty on the solution. And our model relies on the concept of set covering. So the main idea of our method is that first we convert the problem of minimizing Haldor distance to a set cover problem, and then solve the set cover problem using a very fast algorithm. First, let's take a definition of the set cover problem. Here you given a unit set, a universal set U of n elements and collection of subset for S1 up to Sm, where Si is a subset of U. Let's take example. For example, here it would be like the set of n cell, and S1 might be all the T cell from U, and S2 might be all the B cell from U, and so on. And our goal to find the smallest collection of subset of S that cover U. So is it clear? And there is very simple and gritty algorithm to solve this problem. So the idea is that because you need to pick the smallest collection of S, right, that cover U. So first you just pick one element which covers the most element from U. And you remove it from S, and you also remove its elements from U. And you just repeat it until all the points are covered. And despite simplicity, algorithms have a theoretical warranty. This gives you a log n approximation. This means that the solution will be at most log n the size of optimal. And in practice, it's very close to optimal, maybe just like 1.5 or 2 approximation. Unfortunately, this algorithm does not scale well to very large data. And therefore, we employ the faster version of Gritty. It's called disk-friendly Gritty. And it's achieved a dramatic improvement over Gritty. And more importantly, it also gives like an approximation ratio of 1 plus p log n in here, which is p times larger than Gritty. And here p represents the trade-off between the speed and the accuracy. And this is the overview of our method. We call it fetcher. Input, we have an n cell, and output is subset of size k. And our goal to minimize the Haldor distance, right? We want to minimize the furthest point from the sketch. And if it's small, then every point in the sketch will be close to every other point. So this is the main idea, right? And first, we guess the optimal solution. And we'll find later using binary search. And for fixed L, we'll construct a bro of radius L, center at every point. So I repeat, so for fixed L, we just construct a bro of radius L, center at every cell. And our goal to find the minimum number of balls that cover all the points. And we solve it using the DFG algorithm. And in very high level idea, we just select the ball which covers the most of the point here, and we remove it and we repeat until all the points are removed or until all the points is covered. And given the collection of balls in the solution, you just pick the cell at the center. And it might be end up with a greater or lower than K points, and then you need to adjust L to obtain exactly K points or K cells. And here's the summarized main algorithm. So the while loop here just essentially will find the right radius by binary search. And for fixed L, we show the corresponding set cover using the FG algorithm. And more importantly, we have a theoretical quantity for our algorithm. So we show that if we are willing to include slightly more cell in the sketch, then our algorithm will want to find a solution of the optimal radius. And for really large data set which have let's say like 100,000 or million of points, we still need to compute the pairwise distance, and we cannot afford it. That's why we combine this algorithm with a hybrid approach, and the aim to accelerate our method for very large data set, maybe up to like million of points. And the ideas for so first we divide the space into the equal size boxes, and then you just pick 1 point per box at random. And then they apply the same algorithm as before. So we apply the factor, but not on all points, but only on the selected points in the previous step with a careful choice of delta and L. Here delta is the grid size and L is the radius of the ball. And most importantly, we show that only increase the out-of distance by the azimuthal factor of 1 plus epsilon. And I want to mention that our grid sampling is different from symmetric sketching. In here, as opposed to symmetric sketching, our method is just independent of the data. So it's much simpler and it's faster. And now we compare our method to symmetric sketching. And first we compare the out-of distance between two methods across 6 data set and sketch sizes. So in here, sketch size would be like 1%, 2%, up to 10% of the data, of the full data. And for each sketch size, you just run every algorithm 10 times. And note that both symmetric sketching and our method aim to minimize the out-of distance, right? So the smaller, the better. So in here, you can see that in all data set, right, the feature our method are current that outperform symmetric sketching. And so the next question would be, does a better out-of distance translate to better biology, for example? And the answer is yes. So to do it, we show that we compare our method to symmetric sketching in the cell type identification. So this is one of the most important steps in single cell data analysis, and it's often done via clustering. And the idea is that if you have very big data like this, so first you downsample the data to 10%, and then you run the clustering on the sketch using, for example, Leuven clustering, and then you extrapolate the label to the full data using supervised learning. For example, you can use the k-nearest neighbor search. And this result here are shown for the full data. And in here, we use a trusted run index to measure the similarity between the infer clustering and the Gauss truth. And one indicates a perfect agreement between two solutions. And the larger, the better. And so you can see that across most of the data set, we are better than symmetric sketching. And only 3 out of 36 instances, the symmetric sketching is slightly better than our method. For example, in here, they're just slightly better on 3 out of 36. But in most instances, we are much better. And in here, the dotted line indicates the the score on the full data. And you see that remarkably in several instances, our method even better than capturing the full data. And this are not surprise. Actually, this observation is consistent with the assumption of more balanced composition in the sketch. And how dot distance defined on the given matrix space D, but the symmetric sketching ignores the matrix space. But our method takes into account the different matrix. And here we want to show that the choice of matrix is important. And here we investigate the problem on the casting again using the same like RE score to perform to measure the performance. And on the left, you can see that I will run our method for 4 different metrics like Euclidean, cosine, Pearson, and Manhattan. And on the left, you can see that the factor with Euclideans yields the most accurate result. But on the right, it has a poor performance with the Euclideans in red here. But Pearson have a higher hierarchy score. And in contrast, the metric sketching, they cannot distinguish between different metrics, and they yield very low score in overall. And next, we want to show that factor is sensitive to the red cell type detection. So we just reanalyze the umbilical cord blood cell and where the author detect a new cell type using symmetric sketching. And this new red cell type is not visible if you use full data or if you use a uniform subsampling. And here we run our method again on the same data set, and we find this rare cell type using the same marker chains as in the original publications. So this is one of the main highlights of the method, that you just naturally increase the representation of rare cell type and make it easier to be discovered. And finally, we compare the scalability between two methods. And on the largest data set, which consists of 2 million cells, our method only requires 60 minutes, while symmetric sketching needs like 30 minutes. And those are not only we are faster, but we also more accurate, right? And in conclusion, so we just propose a method for downsampling massive single cell RNA-seq data, and the idea to minimize the out of distance. And most importantly, we provide the theoretical advantage in terms of accuracy and robustness. Although we don't show here, but in our paper, we prove that our model is robust to the noise. And more importantly, our method can easily to incorporate the prior information like cell type or correlation time point, and it will help like a trajectory inference better. And we also show that it's benefit downstream analysis like clustering, trajectory inference, and rare cell type identification. These are the main downstream analysis that's in single cell RNA-seq data. And most importantly, we can like this allow to shift the focus from more data, less algorithm to less but accurate data and more algorithm. And for that, I just conclude my talk with the acknowledgement to my supervisor. I would like to thank my PI, Dr. Stephen Kansai, and my collaborator, Khaled. And thank you for your attention. And here's our paper and our tool. So feel free to try it. And thank you. I'm happy to take any questions.